cloud. Okay. So yes, so we should introduce Gregory. How do you say your last name? Wilsenach?
Yeah.
Okay.
No,
Okay, so-
I think that was faster than 3 times speed. That was running through those slides. Yes.
And backwards, really tough.
Yeah. Okay, so I'm supposed to introduce Gregory, but Jamie's quite wise point was we don't all know each other, and I don't actually know Gregory. Are you a PhD student or a postdoc, or like what is your status?
No, Neil, what you should do is introduce Anush, who can then introduce Gregory.
So, should I introduce myself?
Yes, please do. We want to know you.
Okay, so no, I was a PhD student, and as I guess Andy and Anush can testify, I then graduated, and so now I'm a postdoc in the department under Anush. I was working, I guess it goes without saying, given I was under Anush, but I was working in problems in finite model theory and on issues of topics on symmetric computation, which is what we're going to be discussing today.
Okay, well, we'll be happy to hear about it.
Okay. So anyways, as I said, I'm going to be presenting some work on symmetric arithmetic circuits, which was done with Anush Dewar. And so the elevator pitch for the whole topic is, for the research, is that we use techniques from finite model theory to prove lower bounds in arithmetic complexity for a particular model in arithmetic complexity. And so what we did is we introduced this notion of a symmetric arithmetic circuit, and we proved a polynomial upper bound for the determinant, which is an important problem in this context, and an exponential lower bound for the permanent. And if you don't know what any of these words mean, you're not sure what an arithmetic circuit is, you don't know what determinant or permanent are, I'm going to begin by going through a pretty slow introduction to these topics. So in this talk, I want to first sort of introduce, I'm not really sure the level of background on topics in complexity theory that most people here will have. So I'm going to sort of introduce some basic topics in complexity theory and some basic topics in arithmetic complexity, which is slightly more unusual. And then I'm going to discuss how sort of questions about symmetry naturally arise in this context. And then I'll introduce this model that we introduce in our paper, which is a symmetric arithmetic circuit. And then I'll discuss prior work on symmetric circuits, which in some sense is really the motivating work, and the relationship with finite model theory. And then I'll sketch the 2 results I mentioned a moment ago. I'll sketch the proof establishing a polynomial upper bound for the determinant, and I'll sketch our proof establishing an exponential lower bound for the permanent. Since circuits are going to play this really important role in the talk, and in particular 2 different types of circuits, it might be worth describing these things at a quite abstract level to begin with, right? So at its most abstract, a circuit is just let me just move this. How do I move this thing around? There we go. So at its most abstract, a circuit is just a labeled directed acyclic graph, and you have what are called input gates, which are these gates with in degree 0. So here they're in green. And all the other gates are called internal gates, and here they're blue and red. And then there's one designated gate which has out degree 0, which is called the output gate. And normally, I haven't labeled them here, but normally they're labeled by these internal gates and input gates are labeled by things. So if you've, there we go. Wait, what's going on? Okay, so if you have met circuits before in the context of complexity theory, you've probably met what are called Boolean circuits. So here the input gates are normally labeled by some variables x1 through xn. So on the left-hand side, I just have x1 through x3. And the internal gates are normally labeled by Boolean functions. So most familiarly, you'll see and, or, and not, right? And sometimes you'll see, and importantly for the talk today, you'll see other functions like majority. And if you're unfamiliar with majority, it's just a function that outputs a 1 if and only if the input string has at least half of its input being 1, right? And we can think of a Boolean circuit as naturally computing a Boolean function, right? So if a Boolean circuit has n input gates, x1 through xn, it naturally defines a function on n-length strings. And this function is given by simply recursively evaluating the circuit. Right? So you start from the input gates, which now are associated with, for a given input, actually now is associated with an individual bit, and you just propagate forwards. Right? So you go to the next gate, compute the function associated with that gate, and recurse through the whole circuit, eventually getting to the output gate, and that's the output. That's the value of your function for that particular input string. And in complexity theory, we're usually interested in families of these circuits, and a family of these circuits where each Cn computes, has n input gates, naturally defines a language, because you can you have a function corresponding to you have a function that takes in an input string of arbitrary size. For each length of an input string, you have some function that takes in that size string. And indeed, every language can be described by some family of circuits. And one of the ways which, this is a very standard model that's studied in complexity theory. It's really, one of the reasons it's studied is because it's sort of combinatorially accessible and it seems quite nice. And in any event, very popular model in complexity theory, and you may well have met it. A slightly more bizarre notion or unusual notion is the notion of an arithmetic circuit. So in arithmetic complexity, we're interested in the problem of computing certain algebraic problems. And we're interested in computing them, the important, and the way we compute them is slightly more abstract. Rather than looking at Boolean operations, we look at sort of measuring cost in terms of arithmetic operations, so things like plus and times. And the important insight is that many of these algebraic problems can be reduced to the problem of computing some polynomial, or as is often the case in complexity theory, we're interested in doing things asymptotically. We rather think of the problem of computing a family of polynomials. So let me give you an example of an arithmetic circuit. It's a circuit just the same way as defined previously, except now the input gates are labeled by either variables from some fixed set of variables, or field elements from some fixed field f. And the idea is that this circuit describes a polynomial in the ring fx. So on the left-hand side, you can see the circuit. You can see an example of a circuit. So we have two variables, x1 and x2, and we have two field elements, 1 and -3, and we have 3 internal gates, and one just recursively evaluates these gates. And again, one thinks of plus and times as ring operations here, right? So x1 and x2 are elements of the ring, and plus will add x1, the first plus gate will add x1 and 1 in the ring, and you're left with a formal polynomial. And you propagate through, and the output gate will compute or rather represent some polynomial. So this is a slightly different notion of computation than the one you saw in the Boolean context. I mean, here, in some sense, you're computing an object which, since you're operating over a ring, I'm not sure you call it syntactic, but it's more syntactic, right? You're computing a polynomial, not a function, right? And so you don't need to assign any particular values to the input gates. The input gates are themselves labeled by elements of the ring already. So it's this is what's generally considered in arithmetic complexity as a slightly different problem. I mean, if one deals with arithmetic complexity, some interesting problems arise as a result of this. Of course, every polynomial just defines a function. So you can still look at the functions computed by such a circuit. So in arithmetic complexity, a sort of similar thing arises as in Boolean complexity. One begins to define complexity classes, or more specifically, Valiant begins to define complexity classes. So you have this complexity class, the sort of analogous class to P is this complexity class VP, and it consists of families of polynomials that can be represented by polynomial size and degree families of arithmetic circuits. So you can't allow any blow up in the degree of the polynomial. And then there's another class VNP, which has a definition in terms of something that looks like a certificate definition, so it's sort of analogous to VNP. But an alternative definition, which is easier to state, is like roughly this is the class of polynomials such that the problem of computing the coefficient of some monomial in Fn is easy. And I've suggestively drawn the picture over there with, so VNP certainly contains VP. Whether it's strict is an open problem, and indeed this is something called Valiant's conjecture. So, are these two complexity classes equal? And this is the algebraic analog of P versus NP conjecture. So it's a completely essential open problem. And what's interesting about it is it's easier than the P versus NP conjecture in a logical sense. I mean, in the sense that one implies the other. But it's not. What's interesting about it is you get to apply all these tools from commutative algebra and indeed from algebraic geometry to try to tackle it, because now you're working over polynomial rings. So it's an interesting problem all by itself. Now, in this context, there are two families of polynomials that are super important, the permanent and the determinant. And you've all probably heard of the determinant, but I should at least describe how we think of it as a family of polynomials. So here, we define for each n some polynomial det n, which is just the determinant of an n by n matrix of variables. So we have some matrix of variables, xn, where each variable is just xij. And the determinant is just defined the normal way, exactly how you're used to it in linear algebra. The permanent looks very similar, and I'm not sure how many people have even heard of it. It's not anywhere near as ubiquitous as the determinant. And it's defined in the same way. Again, we have for each n a polynomial perm n, which is defined over an n by n matrix of variables. But here, the real difference is just that we skip out the whole sign thing. So there's no plus or minus one floating around. And let me just try to move something if I can. How do I? Okay. The important thing is that the permanent plays a role sort of analogous to the satisfiability problem in complexity theory, in the sense that it's VNP complete. And the determinant is also complete in VP under a slightly different notion of a reduction. And so we often think of the VP versus VNP versus, we often think of the VNP versus VP problem as sort of, sometimes this is called the permanent versus determinant problem. So these two polynomials play the sort of canonical representatives of their two classes. And indeed, showing that they're not equivalent, showing that VP is not equal to VNP is the same as proving that there are no polynomial sized families of circuits that compute the permanent. Right? So proving lower bounds on the permanent is sort of, just as, is the central problem. It's a complete rephrasing of the V not equal to VNP problem, VP not equal to VNP problem. And indeed, I mean, if you just look at this for the first time, I think anyone who comes to the subject for the first time looks at these two families of polynomials and says, but surely the permanent actually looks simpler. I mean, it doesn't have this minus one plus one floating around. So why is it that the permanent is so much harder than the determinant? And I should mention over fields of characteristic 2, because if I'm only interested in fields of characteristic 2, well, then plus minus 1 are the same, and the two polynomials are identical. And sorry, the two functions are identical. So you get, it's its own interesting question. So the way in which we make progress in circuit complexity, but also in arithmetic complexity, is that we look at particular superpolynomial bounds for particular circuits, because we certainly don't have them for any general circuits. If we did, we'd have the conjecture solved. So we're looking at particular classes of circuits, and we're wondering, can we prove superpolynomial bounds in these particular contexts? And so we have exponential lower bounds for monotone arithmetic circuits computing the permanent, for monotone arithmetic circuits computing the permanent. And well, this result was partially proved in 1982 and then later on in 2014. And to give another example, we have exponential lower bounds for depth 3 arithmetic circuits computing the permanent over finite fields. And I just mentioned this as an example because it's interesting to note that the field really matters. I mean, and we'll see this actually in our talk today. It's important to notice that in actual fact, we have these exponential lower bounds for the permanent in these two restricted cases. In actual fact, they apply to the determinant as well, which is a bit of a problem. It really just tells you the model is incredibly weak because we know the determinant can be done in VP. And what we're going to do today is present a new notion of a circuit, a new sort of restricted class for arithmetic circuits called a symmetric arithmetic circuit. And we'll prove an exponential lower bound for the permanent and a polynomial upper bound for the determinant. So we actually do manage to separate them in this model with some caveats, which I'll talk about at the end. And I should mention for those who might be interested in this topic, we have already considered symmetry in questions about symmetry in arithmetic complexity have been considered in another context. There's a paper by Landsberg and Ryser on determinantal representations that also separates the permanent from the determinant, but it's very, very different and motivated by questions essentially coming from the algebraic geometry side of this approach to complexity theory. And there's no obvious way. Let me say that charitably. It seems they're very, very different. There's no obvious way to translate these to get circuit lower bounds. So they're quite a different thing. Okay. So before we talk about these symmetric circuits, let's talk about symmetry in the context of polynomials. So there's already a notion of a symmetric polynomial, which is normally one that's symmetric under all possible permutations of its variables. So it's invariant under any permutation of its variables. And the permanent and determinant are not symmetric in a sense. But they do have certain natural symmetries. So more generally, let's suppose we have some group G acting on the variables. This group action naturally lifts to the ring of polynomials. And we say some polynomial is G symmetric if every permutation in G fixes this polynomial. And it's easy to see, and before I say that, let me say that we can define a similar notion for functions. We often go between the two. So the permanent, as I said, isn't symmetric in the strong sense, but it does have certain natural symmetries. So for example, it's symmetric under taking. Oh, sure, yeah.
What is a permutation in a group?
Let G be a group acting on if every I just mean every element in G fixes P. So in other words, if you take every element in G and you act it on P, it fixes P. So sigma for every sigma in G, sigma P equals P.
So
okay.
So maybe just group acting on a set of variables just means you're treating the group as a permutation group on X. So
yeah,
okay.
Yeah. You just
okay, I see what you mean. Okay, so you just mean applying the group action to every variable. Okay.
Exactly. Okay. So the permanent, as I said, isn't symmetric in the strong sense, but it is symmetric. It does have certain natural symmetries. So, for example, if you permute rows and columns separately for the permanent, you leave it completely fixed. And for the determinant, you also have certain natural symmetries. Here you could look at simultaneous row and column permutations and transpositions as well, but for the moment, let's ignore those. So you can take simultaneous row and column permutation. In other words, for sigma in sum n, sigma maps the variable x ij to the variable x sigma I sigma j. Right? And in this talk, I'm going to fix those two groups. So when I talk about the permanent as being symmetric, I mean symmetric with respect to this group action that permeates the rows and columns separately. And when I talk about the determinant being symmetric, I mean it with respect to this group action that simultaneously permutes rows and columns. Okay, so let's talk about symmetric circuits. And this is sort of a natural way of, we can think of this as a sort of natural approach to computing these symmetric polynomials. And so we say some circuit C computing a G-symmetric polynomial or function is a symmetric circuit if the action of each permutation in G on the input gates extends to an automorphism of the circuit. So let me be clear about that. The input gates of a circuit, remember, are labeled by input gates in an arithmetic circuit are labeled by elements by either variables or field elements. So the natural action for each permutation in G on those input gates just fixes the field elements and permutes the variables according to the group action. And then we ask whether we were interested in exactly those circuits where each one of those extends to an automorphism of the circuit. And an automorphism is exactly what you expect. It's an automorphism of the DAG structure that preserves labeling. So let me give you something of a toy example.
Quick question. Is this for all G that such that the circuit is such that the polynomial is G symmetric?
No, so we fix a group.
Okay.
So of course the polynomial may be symmetric with respect to lots of different groups.
But this definition is just with respect to one G.
Exactly. So,
Okay.
So a slide ago when I said I want to fix the group for the permanent and the determinant to be those particular groups, I mean, of course, they're symmetric with respect to different groups, right? I mean, as well. So that's certainly the case. And of course, Well, I'll talk about that towards the end. It becomes an important factor. So to give an example, suppose we have a circuit that looks something like this, and I just left out the labelings on the internal gates. And we have some permutation that just swaps X and Y. And we can act that on, that act naturally on the input gates. And the circuit automorphism that would correspond to that permutation would be the circuit automorphism labeled in pink. So you would have to swap those two gates to get the corresponding circuit automorphism, right? So the circuit automorphism induced by this permutation would look like this. But if we tried, for example, to look at the permutation YZ, it's not too hard to show that this doesn't extend to an automorphism of the circuit. Okay, and the important concept I'm going to need later on is the notion of an orbit of a gate. And so the orbit of the gate is just all possible images of that gate under all possible images of the gate pi g, where pi g is just an automorphism extending some permutation. Okay, so since the permanent and determinant are so important, I should probably emphasize exactly what's, I should probably look at those cases in particular, just to make sure this is well understood. So the permanent looks something like this. I mean, each polynomial in the family of permanents looks like this. And we're interested in permutations of this sort acting on the variables, right? So we're interested in sim n's cross sim n acting on the variables. And so when we look at circuits, what that means is we're going to map each xij to x sigma I pi j, and we're going to require that each one of those permutations extends to an automorphism of the circuit. Okay, and similarly for the determinant, we're interested in just the action of sim n, and again, we require each permutation that looks something like this extends an automorphism of the circuit. So hopefully that's clear. Now, an interesting example to look at is Ryser's formula. So, the best known upper bound for the permanent is given by this formula called Ryser's formula that looks like this. And importantly, this is a little bit, it's an exponent. If you implement this as a circuit, you get something that's exponential. And importantly, the sort of natural implementation is also a symmetric circuit in the sense we mean it. And so this is kind of nice. It tells us firstly that our definition of a symmetric circuit seems quite natural. These crop up already in the subject. But moreover, it sort of begs the question, can we match that upper bound with a lower bound? And indeed, we get close. We don't quite get exactly that lower bound, but we get very close. Anyways, now I should, at this point, pause and talk a bit about Boolean circuits. So, I mean, in many respects, I talked about symmetric arithmetic circuits emerging from asking questions about symmetric polynomials. In some sense, this is a false history. I mean, in reality, symmetric circuits first emerged in the context of finite model theory via work by Derenberg and later Martin Otto and later Anderson and Dewar. And in this context, they were particularly interested in circuits where the input gates, where the circuits take in relational structures. And the input gates are labeled by potential tuples in the relations. So if we think about graphs, for example, the input gates would be labeled by, so if you're looking at a circuit that takes in a graph of size n, the input gates would be labeled by potential edges in that graph, right? So tuples ij. And the permutations they're interested in are permutations on the universe and the induced action of those arbitrary permutations on the tuples. So in other words, the action of sim n on the tuples. It's the same action we looked at for the determinant. And so they're interested in these permutations, and they define symmetric circuits to be those that such that each one of those permutations extends to an automorphism of the circuit. And the reason why this is interesting is in the context of structures. These circuits are guaranteed to compute isomorphism invariant functions, right? So, or if you think of them as deciding classes of structures, they decide isomorphism closed classes of structures. And indeed, in some sense, the symmetry condition can be seen as a sort of syntactic condition guaranteeing this fact. And this is sort of why they're interested. And in particular, they arose in the reason they were interesting to people in logic was that there's a sort of natural connection with finite model theory. And the important result along these lines is by Matthew Anderson and Anuj, which asserts that P-uniform families of symmetric circuits with majority gates. In other words, you allow and, or, not, and the majority function. And P-uniform just means that the function that takes n to the circuit Cn is computable in time poly and n. Now, if you look at those, the classes of structures that are definable by these circuits, it's exactly the same as the class of structures that's definable by a logic called FBC, fixed point with counting, which is a sort of canonical logic in finite model theory, which has all sorts of interesting connections and a very interesting logic. It sort of, in a technical sense, almost captures polynomial time, but not quite. A really interesting logic. And there's an analogous non-uniform result. So you can drop uniformity condition, and you can sort of look at a, if you like, non-uniform analog of FPC. And I need to introduce that slightly more formally. So let's CK omega infinity omega be infinitary first order logic with counting quantifiers using at most k variables. So let me say what that means. So in other words, formulas of CK omega infinity omega can have infinite disjunctions and conjunctions. You can only use variables from x1 through xk. And you can have these things called counting quantifiers, which look like this. There exists greater than or equal to k, and then you bind a particular variable x. And the semantics is sort of what you might expect, which is that there are at least k x's satisfying this formula, or at least k assignments to x that satisfy this formula, right? So this is what this logic is. And
Greg, just you're using k in more than one way in that. The quantifier, the k and the quantifiers can be arbitrary.
Sorry, yes.
It doesn't have to be the k of the logic.
No, you're completely right. Sorry, that's a mistake on my side. So the quantifiers can be of the form. I mean, so I really mean you have a family of quantifiers for each possible threshold you want to consider, right? So it should be greater than or equal to t for any t, a natural number. We're often interested in the logic that just contains all of these. So you just take the union of all these things. We have C omega infinity omega. And the non-uniform result from Anderson and Dewar establishes a connection between the computational power of symmetric circuits with majority, and now instead of placing a bound on instead of putting any uniformity condition or a bound on the size of the circuit, we put a polynomial bound on the size of the orbits. So it's sort of a local polynomial condition. And these families of circuits have exactly the same power as C omega infinity omega. And now if you haven't met finite model theory, this might not be that interesting. I mean, you now get this lovely connection between counting logic and symmetric circuits, but sort of the natural question would be why? And the basic idea, if you've met this before, is that this is kind of wonderful news. If you can connect anything with C omega infinity omega, you're in a good place, because we have really powerful techniques for proving lower bounds, proving inexpressibility results of this logic. And so this connection with symmetric circuits means that we can establish inexpressibility lower bounds for symmetric circuits. Yeah, somebody had a question?
Yeah, I do. I have a question about the meaning of these counting quantifiers. When you say exists greater than or equal to k, does that mean like there are at least k assignments to this variable, or?
Yeah, at least k assignments to the variable such that the formula is true, right? So there exists greater than or equal to k x phi would be, there exists at least k distinct assignments to x such that phi given that assignment holds. Okay.
So it's not second order logic, but it's like a little bit more than just plain first order logic.
Yeah, I mean, of course, you can sort of replicate these things if you don't actually have a variable restriction, right? These are only interesting in the context of the variable restriction. Okay. Otherwise, just chain together a bunch of existential quantifiers and just say they're all different. Cool. Okay, so I mean, if anyone else has any questions, particularly around this topic, I appreciate that I'm sort of rushing through some technical detail here. So, please do stop me. But anyway, so this is great stuff. This means we can prove inexpressibility results. But now let me actually, I've been talking a lot about background. Perhaps I should actually start talking about results. Well, mixed in with some background. So before we get to the lower bound, let me talk about the upper bound. So the result for the determinant we have is that if F is a field of characteristic 0, then we can, then there are families of arithmetic circuits that compute the families of symmetric arithmetic circuits that compute the determinant over F that are cubic in size. And the sort of one-line description of what you do is you sort of use Lever's method. And so let me flesh that out slightly. So you recall the characteristic polynomial of an n by n matrix looks something like this. And the important thing to recall is that that Pn over there is in fact the determinant of the matrix. And Lever's method really just gives a recurrence relation for each of these coefficients Pn in terms of these SIs, where each of these SIs is really just the trace of the ith power of the matrix. Okay, so in other words, you can compute the determinant by just implementing this recursive relation and just computing PM. And this can be done quite naturally via a symmetric arithmetic circuit as follows. You just, for each I, you just compute the power. This can be done symmetrically, and you just take the trace. Again, this can be done symmetrically, and then you just, iterate this process and compute PM. I mean, it's really obvious implementation. And the slightly, the thing to observe is that those recurrence relations require division by arbitrary numbers between 2 and n. And so it's really, it's not obvious how you would have to alter the method in order to make this work for finite fields, and it's really not obvious that you can. We found one paper that claimed to, but the method that does, but the method they use breaks symmetry at some point. Okay, so now for the sort of main result, that'll be the rest of the talk, and that's the lower bound for the permanent. And so the formal statement of this, which isn't actually the formal statement in the paper, but it has since been strengthened, is that if you take any field of characteristic other than 2, there's no family of symmetric circuits over that field of sub-exponential size computing the permanent. Nice, clean result. And the sort of first insight you have to have is a sort of elementary observation about the relation between perfect matchings and the permanent, which is that the number of perfect matchings in a bipartite graph G is equal to the permanent of the bi-adjacency matrix over Q, indeed over any field of characteristic 0. And so we prove the main theorem in 2 steps. First, and this is a bit of a mouthful of the phrase, we show that if you can compute the permanent via using a family of symmetric arithmetic circuits with some orbit bound S, then you can check whether the number of perfect matchings in a bipartite graph is equal to some constant K using a symmetric Boolean circuit with the same size orbits. So you can sort of reduce the problem, the arithmetic problem, to a problem in the Boolean world. And you preserve orbits while you do it. You preserve orbit size while you do it. And then once you have that available, you can prove an exponential lower bound in the symmetric Boolean case using techniques from finite model theory. So in particular, you use results establishing an expressibility of this problem in counting logic to establish this result. So let me first talk about this translation from arithmetic to Boolean. So the formal statement of the theorem I just said a moment ago looks something like this, which is just a complete restatement. And in particular, notice that what we're looking at is all possible 0-1 assignments to the inputs. And we're thinking of the arithmetic circuit now as computing a function. And we're saying, suppose we start with some arithmetic circuit. And suppose we have some K, an element of the field. It follows then that there's a symmetric Boolean circuit C that's symmetric in exactly the same sense, that has exactly the same variables. And the symmetric circuit C outputs a 1 if and only if the arithmetic circuit evaluates to K for the same input. And importantly, C has the same sized orbits as the arithmetic circuit phi. In actual fact, as an aside, it in general blows up exponentially, but the orbit size is preserved. Okay. And I mean, roughly speaking, the idea looks something like this. You observe that for each gate in the arithmetic circuit, since you're only looking at 0-1 assignments, there's only a finite number of possible values that gate could take on for a given input, a given 0-1 assignment to the variables. Right, so if you actually compute the function at that gate, there's only a finite number of possible values it could take on given that there are only 0-1 assignments you're considering to the input variables. And once you have that, you start recursively constructing this Boolean circuit, where for every G in the arithmetic circuit, you compute this CG in the Boolean circuit. You compute a Boolean circuit, you construct this Boolean circuit CG, and it has an output gate for every possible value G could take. And each of those output gates evaluates to 1, if and only if the arithmetic circuit, so the gate GQ evaluates to 1, if and only if the arithmetic circuit would have evaluated to Q for that same input. This is a mouthful to say, but it's a reasonably straightforward concept. I mean, it's just really the Boolean circuit is just doing the checking, and at each recursive step, you just output it. You have a single for each gate in the arithmetic circuit, you have a family of gates, each one of which checks what value that gate in the arithmetic circuit would have evaluated to. And then you just take the appropriate output gate. You fix one of them HK, and you fix that to be your output gate. And that suffices to construct the whole Boolean circuit. So that's one step. And if you just take away anything from this, the idea is you can translate this arithmetic question to a Boolean question. So the next concept that I need to introduce here is this notion of counting width. So for each k, let that equivalence relation, which we'll just write as CK equivalence, denote indistinguishability. So it's an equivalence relation on relational structures, or for the moment, let's just suppose it's an equivalence relation on graphs. And it just denotes that the two graphs are indistinguishable by any formula in CK omega infinity omega. Right? So phi, for every phi in CK omega, phi is true of G if and only if it's true of H. Okay. And we can think of this equivalence relation as something that over-approximates isomorphism, in the sense that if G and H are isomorphic, then they're definitely going to be CK equivalent for any k. And importantly, these equivalence relations are refined. As you increase the k, you get a more and more refined relation. And ultimately, once you get to the size of the graphs that you're actually considering, well, now you do get isomorphism for those graphs. Importantly, though, there's no fixed k such that CK equivalence corresponds to isomorphism exactly. In other words, G and H are isomorphic if and only if G and H are CK equivalent. And this was resolved in the 1990s by Seyfier and Immermann in a very famous paper using an important construction I'm going to mention in a moment. So a graph parameter is just an isomorphism closed function from a class of graphs to some to the natural numbers. So there are obvious natural examples of this: the chromatic number, the number of perfect matchings, the number of connected components. These are all graph parameters we're all very familiar with. And we talk about the counting width of a graph parameter. So suppose we have some graph parameter mu. The counting width is some function nu that's defined such that nu of n is the smallest k, such that if G and H have size n and they're k equivalent, then the graph parameter on G and H, the graph parameters on G and H are the same. And this is an incredibly important notion here. And we also talk about the counting width of a class of graphs, and counting width of a class of graphs, just the counting width of its indicator function. And in the context of logic, we're normally interested in two cases in particular. We're interested in the case where we know that the counting width of a graph parameter is bounded by some constant. So we know it's at most 5 or 6 or 7. And this tells us that this means that we have some hope of expressing it in CK in a logic with k variables. And of course, if it has unbounded counting width, it means there's no hope of expressing it in any one of in C omega infinity omega. It's inexpressible in C omega infinity omega. So that's normally what we're trying to show, is that there's unbounded counting width, and that's how we establish these lower bounds. So some examples of unbounded counting width graph parameters are the classical Hamiltonian graphs, or the graph parameter that computes the number of 3 colorings of a graph. These are unbounded and indeed have linear lower bounds. And examples of classes of graphs with bounded counting width, the number of connected components, and interestingly and highly non-trivially, graphs with at least one perfect matching. So we know that we can compute that via some, we know that problem is expressible in CK omega infinity omega for some k. And what's interesting about that is, we're going to show today that the graph parameter the main result we mentioned a moment ago tells us that the graph parameter that, the way we're going to prove the main result is by establishing that in actual fact, the graph parameter that maps a graph to the number of perfect matchings in that graph has unbounded counting width. So, if you just ask whether it's non-zero, we can do that. But if you ask what actually it is, we can't do that. Okay, so let me talk about the overall approach. So the key result we're going to use is something called the support theorem. And this is what it establishes the connection between counting width and orbit size. So what this says is, if you have a family of symmetric Boolean circuits with majority with sub-exponential orbit size, then the counting width, that decides some class of graphs, then the counting width of that class of graphs is sublinear. Okay, and that means we can establish exponential low bounds on some exponential low bounds for some problem by showing that the counting width is at least linear. So we're going to be interested in, so let mu0 be the graph parameter that maps a graph to the number of perfect matchings in G. And for a prime P, let mu P be the residue of this modulo P. So as I said, to prove the main theorem, we just need to prove a linear lower bound on the counting width. And once we have a linear lower bound on the counting width, we have an exponential lower bound on the size of the orbits for the Boolean circuits. And then by the earlier observation, we therefore have an exponential lower bound on the size of the arithmetic circuits deciding this problem. So we just need to prove that we have a family of graphs that witness this fact, that in actual fact there is a linear lower bound on the counting width. And this is where we use a famous construction, and we show that for every k, there's a pair of balanced bipartite graphs x and y that have on the order of k vertices that are k equivalent, but the number of perfect matchings on these two graphs is different, and in fact differ by a power of 2. And this suffices to prove our main result, and this is really what I'm going to be talking about for the rest of the talk. I'll roughly speaking, be talking about how you actually prove that. How much time do I have? Okay, not too bad. Okay, so I'll talk firstly about quote unquote the CFI construction. This is the construction we're going to use to actually build these families of graphs. And I put V in inverted commas because at this point it's like its own field. I mean, it's really a family of constructions, and people go in all sorts of directions. But this is the idea. You start with some graph G that's 3 regular and 2 connected. And you define 2 graphs, the first of which we call the even graph, which we write xg. And we construct this graph by replacing the vertex V with this gadget. And what we've done is we've taken each edge from V and replaced it with 2 vertices. So F is replaced with F0 and F1. And the gadget consists of 4 vertices, 1 vertex for each even-sized subset of the edges. And the idea is that for each of these edges, let's take F0. Notice that F0 and F1. Notice that F0 is connected to exactly those edges that don't have an F, and F1 is connected to exactly those vertices that aren't labeled with an F, and F1 is connected to exactly those vertices that are labeled with an F. And it's the same for the other ones. So that's how you build this gadget. And then we also build another graph, tilde xg, which we call the odd graph, which is defined exactly the same way, except in this case, we select one special vertex in G. And instead of replacing it with this gadget, we replace it with something that looks very similar, except instead of looking at the even size subsets, we look at the odd size subsets. We add an internal vertex for each of the odd subsets. And otherwise it's defined in the same way, and this is called the odd graph. And so long as you start with some expanded graph construction to ensure that the graphs have certain properties, you can construct for each x a suitable G such that the odd and even graphs are k equivalent, but are not isomorphic. And importantly, in actual fact, they come from a class of graphs such that determining whether the isomorphism problem is polynomial time decidable. So this gives you an example of a problem which is polynomial time decidable, but has unbounded counting width. And in fact, at least linear counting width. Unfortunately, these 2 graphs have the same number of perfect matchings. So there's no hope here of just immediately proving the result. We need something a little bit more. And so, we have a CFI construction that looks very similar. Again, you start with the same graph. Again, you have even and odd graphs, but notice there's an important distinction. We've added a little vertex VB that's just connected to every single internal vertex, right? And that's the only distinction. It's a really small, subtle change, but that changes everything. Now we call these orange vertices, those the internal vertices. And since we're, so IV is the internal vertices for the vertex V. And again, using exactly the same approach, you can prove that these 2 graphs are going to be k equivalent and non-isomorphic. And the rest, and really the innovative part, or a huge part of the innovative part of the paper, is the combinatorial argument. Now, how do you count the number of perfect matchings in these 2 graphs and show that in fact they do differ by a power of 2? And that's what the rest of the talk is going to be about. Okay, 10 minutes. 10 minutes. It'll work hopefully. Okay, so the first insight is we divide the perfect matchings into two types. So let's say we have some graph X that's either the odd or even one, and suppose we have some perfect matching. We say it's uniform if for each of the edge vertices E0 and E1, exactly one of them is connected to an internal vertex via the matching. So in other words, you have something like this. If the matching is in yellow, notice that F0 isn't connected to any of the internal vertices via the matching, but F1 is. Similarly, G1 is connected to the internal vertices, G0 isn't. Right? So in each case, we can either pick G1 or G0, F1 or F0, H1 or H0. Exactly one of them must have a matching to the internal vertices. Right? We call these uniform matchings, and the other ones are non-uniform. And it's possible to show that the number of non-uniform matchings in these two graphs are the same. So the really interesting question is, how can we count the number of uniform perfect matchings? And to do this, we sort of use this concept. We count these using what are called orientations. So an orientation of a graph is just a directed graph formed by picking a direction for each edge. And the idea is that uniform matchings, in a meaningful sense, sort of induce an orientation on the graph. In the sense that, let me draw the picture here because it's a little bit of a mouthful to say. So in the sense that suppose you have two vertices, U and V, and you look at the corresponding gadgets. Well, because we're looking only at uniform matchings, exactly one of the two, so we have two edges between them, say two edge vertices that lie between them, right? So the edge between them, E, has been split into two edge vertices, E0 and E1. And because it's uniform, we must have a situation where either E1 is connected to an internal vertex in IV, and E0 is connected to an internal vertex in IU via the matching, or vice versa. Those are the only two options, and this gives us a natural way of sort of deciding an orientation between them. So the nice thing about uniform perfect matchings, they give rise to these orientations. And in fact, the opposite is true as well. So every orientation you can pick, you can construct some perfect matching that induces that orientation. And so we write G, for an orientation, we'd write G with an arrow on top to notice that this is an orientation of G, and we write G with an arrow on top M to denote the orientation induced by the matching M. And so again, now we've reduced the problem. To count the number of, we now need to count the number of total orientations, that's easy, and the number of distinct uniform perfect matchings that induce each of those orientations. And then we've counted the number of perfect matchings in the graph. So how do we count the number of perfect matchings that correspond to a particular orientation? So we start off with some graph, again, it's the even or odd graph, and let's fix an orientation. We want to count the number of perfect matchings that induce that orientation. And again, it's sort of the natural thing to do. You start looking at the individual gadgets and you start building up the perfect matchings by looking at perfect matchings on each gadget that sort of agree with the orientation. Okay, so there's a lot of detail in that, but again, like you have some orientation. If it goes, suppose it goes from V to, suppose you have an orientation that goes, which gives the direction U to V for vertices U and V. Well, you need to make sure that the perfect matching you pick for the gadgets U and the gadgets V agree with this orientation, but otherwise you can pick lots of different orientations that might work. And it's not too hard to show that if you look at a gadget, the perfect matchings in that gadget either are all subgraphs, or all contained in the subgraph T, or all contained in the subgraph S. And they're either going to be, they could be contained in a different subgraph, but they'll be isomorphic to either T or S. So we just need to analyze these two graphs, T and S, and look at perfect matchings in these two graphs. And this will tell us the perfect matchings that could exist in a particular gadget. And then we can build up the perfect matchings in the whole graph by just building them up from there. So let's look at T and S. So what we find is S has 4 perfect matchings, 1, 2, 3, 4. And T has 2 perfect matchings only, 1, 2. And now we think about these odd and even graphs. And it's not too hard to show. Let's suppose we pick some vertex in the graph G. If V is not the special vertex, then V is going to be, I skipped ahead slightly. So V is going to be a T vertex in X. And what that means is that the perfect matchings on V are going to be subgraphs of the graph T. Are going to be contained in the subgraph in the graph T. So V is going to be a T vertex in X if and only if V is a T vertex in X tilde. In other words, it's going to be a T vertex in the even graph if and only if it's going to be a T vertex in the odd graph. But if V was the special vertex, then there's a flip. If it's a T vertex in the even graph, it's going to be an S vertex in the odd graph. So the odd and even, at the point where you get this weird vertex where things have been flipped, you're going to have perfect matchings that either come from the subgraph T or the subgraph S, and they're going to, in the case that you look at the odd vertex, it's going to be a flip. And since there are a different number of vertices in these two, so different number of perfect matches in these two cases, the result when you start doing the calculation is that the number of, for a fixed orientation, the number of uniform perfect matchings is going to differ by a power of 2, because you're going to have this factor of 2 introduced by flipping the number of perfect matchings at the special vertex. And I'm not going to go into the details of the calculation, but so this is what completes the result. So I mean, in summary, this is the end now. So in summary, we introduced this notion of a symmetric arithmetic and symmetric arithmetic circuit in arithmetic complexity, and we established this upper bound for the determinant and proved an exponential lower bound for the permanent as well, which in some sense separated the two. And I'll add a caveat in a moment. And there are all sorts of natural questions about what comes next. So the first thing is, we prove the lower bound for the upper bound for the determinant only over fields characteristic 0. Can you do it for other fields? For finite fields as well, can you also get a polynomial size circuit? And the next question, I think, is the more important one, which is, the first thing you might have noticed is that the groups we're considering are different. And for the permanent, that's not a problem, because if you prove, well, it can be a problem for the permanent, but let me just say in what sense it's not a problem. If you prove it with respect to particular group G, you necessarily have the same lower bound for every group, every supergroup of G, right? So you could take so we necessarily have this lower bound for the group consisting of all permutations, the actual symmetry group for the permanent, which is a much larger group. But in the determinant's case, it's certainly not the case. I mean, we would really like to know whether you could extend this group, right? So, and you could still get lower bounds. And in actual fact, we have a result at the moment proving a lower bound in this case. So we don't think you can still get a polynomial upper bound if you look at the whole symmetry group for the determinant. But for the permanent, we're still interested in, well, what if you consider smaller groups, right? I mean, for larger groups, we have the lower bound, but what about smaller groups? And as I said, for the determinant, does this hold for large groups? And we have a result that suggests not. I mean, it's not complete yet, but we think it's not. And can we improve the lower bound for the determinant? Sorry, the permanent to actually match Ryser's formula? Because that would be really neat to show that Ryser's formula, this natural approach, is really the best hope of a symmetric, the best possible symmetric circuit for computing the permanent. And so that's it. I hope I didn't go too long. That's the end of the talk. Any questions?
Okay, could we all unmute and then thank Gregory? Okay, Anuj, do you mind managing the questions? I have to run to my next meeting right now.
No worries.
Okay.
Are there any questions? If there are questions, you can just speak up.
Okay, so it was either impossible to understand or very easy. I have a suspicion that it jumped from one to the other at some point.
Yes, I'm just puzzling with I've been made the host of this meeting and suddenly a whole bunch of new controls appeared on my screen. I'm just trying to get to grips with them. But okay, I mean, I think if there are no questions, don't think it's my place to ask questions, but
I have a suspicion of what question you might ask anyways.
All right, okay. Well, I think if there are no questions, we'll just thank you again, Greg. That was a very nice talk, I thought. Okay.
Did you catch
All right.
it? Did it make sense?
And I think we'll be back next week at this time. All right.
Okay. So thanks very much.